Hey there folks, and welcome back. I have one last lesson for you on gradients, and this is a cool one. It ties together the material we've been covering recently with the stuff that we introduced at the very beginning of the course. This topic, gradient fields, is not going to be a central focus in Math 119. But if you go on to take a course in, say, vector calculus, knowing a bit about gradient fields will be really helpful. So, cast your mind back to week 1 of our course when we talked about graphing multivariable functions. To produce a 3D picture like this, we started by using a contour plot to get a 2D representation of our graph. This is a collection of our level curves, right? The curves that we get by slicing our function at various heights. Normally those curves are labeled, but in this case it looks like they're color-coded. It allows us to build up the 3D function from a 2D image. The contour plot is one way to do this, but now that we know a bit about gradients, we have another method as well. Remember that the gradient of a function f from r2 to r is really a function itself. It takes in two inputs, x and y, and spits out a vector, the gradient at xy. We can plot that vector at the point xy in the xy plane. Maybe it'll look something like this. By plotting more and more of these vectors, you get a picture that looks something like what I have here. And this is what we refer to as a gradient plot. What is this picture telling us? Well, think back to the 3 properties you know about gradient vectors, particularly property 1. It says that the gradient always points us from xy in the direction of steepest ascent. So what do you notice about the gradient vectors in this picture? Well, one thing I notice is that all of my gradients are pointing me toward the origin. They're telling me that no matter where I'm standing in the xy plane, I can increase my altitude most rapidly by moving towards 0, 0. And you can see that in our picture. We can also get some information from the lengths of these vectors. Remember that if we're moving with the gradient, it's the length or norm of the vector that tells us our rate of change. So if we have a very large gradient, we have a big rate of change. If we have a small gradient, we have a small rate of change. In this picture, it looks like the rate of change is going to be largest when we're farther away from the origin. But when we approach 0, 0, things start to slow down. Again, you can see that in our picture. If I stand at this point here, far from the origin, then when I move towards 0, 0, I experience a big rate of change. As I get closer, however, the rate of change begins to diminish. Before we jump into some more examples, I'd like to show you a cool connection between our contour plot and our gradient field. If I plot both of these on the same xy plane, it might look something like this. Notice anything interesting? In the picture, you can see that the gradient vectors sit perpendicular to their level curves. This was our third and final property about gradients from the last video. In this example, I've given you a new gradient field, and I'd like you to think about what the graph of the function might look like. Well, this looks pretty similar to what we had before, except now I can see that my arrows are pointing away from the origin. It's telling me that no matter where I stand at a point xy, I can increase my altitude most rapidly by moving directly away from 0, 0. So if what we had before was a downward opening paraboloid, maybe now we have an upward opening paraboloid. This graph certainly looks like it would fit the bill. If I stand at a point xy and move directly away from the origin, yeah, I'm going to experience the most rapid rate of increase. But how do we know that it's this graph and not something like, I don't know, this cone? This cone also has that same property. If we stand at a point xy and move directly away from the origin, we're going to experience the greatest rate of increase. The key here is that we should be paying attention not only to the direction of the arrows in our gradient field, but also to their lengths. You can see here that the arrows start out small, which means I'm experiencing a small rate of increase as I move away from the origin. But they get larger as we get farther away, so our rate of increase is increasing. And that's what's going on in this picture. I move farther away from the origin, my rate of increase becomes more rapid. The cone doesn't have this property. As we move farther away from the origin, our rate of increase is constant. So our cone doesn't match the gradient field shown here. Instead, the gradient field for the cone might look something like this. You can see here that we still have arrows pointing away from the origin, indicating that we're increasing in these directions, but now the length of the arrows is constant. We have the same length no matter where we compute our gradient vector. So the cone matches this gradient field, whereas the paraboloid matches this gradient field. Okay, I have two more examples to wrap up this video. In the gradient field on the left, you can see that all of the arrows are pointing downward, right? They're sort of flowing in the direction of the negative y-axis. That means that if we decrease our value of y, we're going to be increasing the value of our function most rapidly. What do you notice about the lengths of these vectors? Well, one thing I notice is that along every horizontal line, it appears the arrows are roughly the same length, which means that my points are experiencing the same rate of increase along these lines as we move toward the direction of the negative y-axis. I also notice that the arrows get smaller as we approach the x-axis from above, and then begin to increase as we move away from the x-axis. This means that if we move toward the x-axis from the positive y direction, our rate of increase is quite large, and then it starts to slow down. When we then move away from the x-axis in the negative y direction, our rate of increase is going up, 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 up. So maybe my function looks something like this. You can see that as we move in the direction of the negative y-axis, we're increasing very rapidly, then we slow down when we get to the x-axis, and then we increase very rapidly again. Furthermore, the rate of change appears to be the same along every one of these horizontal strips. What about this crazy-looking gradient field? This one's a little bit more complicated. Okay, well, one thing I notice is that my arrows are pointing toward the origin along the positive and negative y-axis. This means that if I approach the origin from these directions, my function is increasing. Furthermore, since the arrows are getting smaller, it means that my rate of increase is slowing down when I get close to 0, 0. The opposite is true in the x direction. My arrows are pointing away from the origin along the x-axis, and they appear to be getting longer as we get farther from the origin. So our function is increasing in these directions, but it begins to increase more rapidly the farther we get from 0, 0. Now, there's a lot going on in this picture, so it might not be completely obvious what the graph will look like, but with a bit of imagination, you might arrive at a picture like this. As we approach the origin from the positive or negative y directions, you can see that we're increasing, but our rate of increase sort of slows down when we get close to 0, 0. If we move away from the origin in the x directions, you can see that we're increasing and our rate of increase is going up. This is what we call a saddle surface. Can you guess why?